I welcome you all to this new lecture session. This is on refrigerants. We are going to discuss primary and secondary refrigerants, thermophysical properties, and environmental concerns regarding the refrigerants. My name again is Dr. Mohammed Shamul Haq, and we are going to discuss today refrigerants. At the end of the lecture, you should be able to recognize different types of refrigerants and their numbering system and their environmental concern, and what are the selection criteria for any refrigerants for a refrigerating system or air conditioning system. So let's get started. So this is refrigerants, primary and secondary refrigerants, thermophysical properties, environmental concern, etc. So refrigerants, primary refrigerants are those fluids which are used directly as working fluids. These fluids provide refrigeration by undergoing a phase change process in the evaporator. So that is the difference between a primary refrigerant and a secondary refrigerant. It is the primary refrigerant which actually works as a working substance, and it actually does go through the phase change process, while secondary refrigerant is only getting the energy absorbed from the primary refrigerants and then circulating it into the building, into the factories or the air conditioning space. So secondary refrigerants are those liquids which are used for transporting thermal energy from one location to the other. They themselves do not go through the phase change process. Instead, they absorb heat energy from the primary refrigerants and then transport it to the other parts of the air conditioning system. These refrigerants do not undergo phase change as they transport energy from one location to the other. The commonly used secondary refrigerants are the solution of water, ethylene glycol or propylene glycol or calcium chloride. These solutions are known under the general name of brines. So the common secondary refrigerants are water and a mixture of water and salt, or water and glycol, as water and glycol solution. So those are the secondary refrigerants. The advantages of using secondary refrigerants are several. Some of them are listed here. Number one is the amount of primary refrigerant used can be minimized. If you have to cool a large building, so you might need a larger amount of refrigerants to go through the phase change process and expel the heat, absorb the heat from the building and then expel it out. But instead of that, you can do it with a smaller amount of refrigerant using a secondary refrigerant. That's the advantage of the secondary refrigerant. Primary refrigerants remains in the plant room under supervision. If you are using a refrigerant which is either toxic or which is flammable, then it is better not to send that refrigerants throughout your plant or building, because it may be dangerous. So instead of that, for example, ammonia, instead of sending ammonia throughout the plant or the building, it's better to use ammonia in a chiller and then send the chilled water or the chilled brine throughout the building. So that way it is safer. Pressure losses in the vapor compression cycle are minimized, of course, because your original refrigerant is running on a smaller circuit, so the pressure loss will be smaller as compared to, because the secondary refrigerant, you don't need to compress it, you only pump it throughout the building, so the energy required for pumping will be smaller. So the bigger circuit is the secondary refrigerant, which is working on the pump, and the smaller circuit is the primary refrigerant, which is working on the compressor. Hence the losses pressure losses will be smaller. Hazardous primary refrigerants ammonia can be used for applications such as air conditioning and food refrigeration. As I said earlier, if you're using a refrigerant which is toxic or which is flammable, then it is better to use it with a secondary refrigerant, so that you can keep a control of the movement of your primary refrigerant, and secondary refrigerant can go around entire building and transport the heat energy. So disadvantage: sensible rather than latent heat gain requires larger cooler for a given heat exchange duty. Higher mass flow rate is in comparison to primary fluids. Of course, they are latent heat. The amount of latent heat required by these secondary refrigerant is smaller. So they are basically working on the sensible heat, not the latent heat. The sensible heat is more used, because the water used in the chiller is not going through the phase change process. It is only getting colder to 7 degree or 10 degrees centigrade, and then that chill water is sent around. So it is the sensible heat which is required. For that you need a larger mass flow rate if you just work on the sensible heat. So that is the disadvantage with the secondary refrigerant, because you have to use larger amount of it. Larger mass flow rate will be required. So moving on, these are the two circuits that is explaining how the primary and the secondary refrigerants are used. In the first circuit, we are using a secondary refrigerant. So the primary refrigerant is basically cooling this chiller. The primary refrigerant is coming up to this chiller, up to this heat exchanger, and in the heat exchanger, up to the heat exchanger right here, and the heat exchanger we have the secondary refrigerant circulating. So it will absorb the heat from the primary refrigerant, and then that secondary refrigerant will go throughout the building, throughout your plant. So this is your plant. This will go throughout your plant, and it will keep circulating in that way. So it will be absorbing heat or absorbing energy from the primary refrigerant, and then it will go to the building and transport it. So this is indirect refrigeration, where a secondary refrigerant is used along with the primary refrigerant. And whereas in the second example, in the second one, we are using only the primary refrigerant. Direct refrigeration. The second one is the direct refrigeration. We are only using primary refrigerant. So this is the condenser, and this is the compressor. So after compressor, it will after the condenser, it goes to the building. The primary refrigerant is going to the building, it absorbs the cooling load, and then it goes to the compressor. And so the entire circuit is based on the primary refrigerant only. It is your refrigerant which is circulated. There is no secondary refrigerant. So these are the two ways. One is utilizing a primary refrigerant on the top, and the second one is not utilizing a secondary refrigerant. So that is the difference between the two circuits. Okay, moving on. What are the comparison of primary and secondary refrigerant? Number one, primary refrigerant will undergo a cycle of refrigeration. So it will undergo a change in the phase, and while secondary refrigerant does not undergo a cycle of refrigeration. It doesn't go through the cycle of refrigeration. It is simply transporting the energy from one place to the other. Okay, primary refrigerant is capable of higher refrigeration effect. It is capable of lower refrigeration effect, because this one, the primary refrigerant, is involved with the latent heat of vaporization and condensation, but here it is only sensible heat which is working. So primary refrigerant is expensive, while the secondary refrigerant, water or brine solution, they are relatively cheaper. Leakage is a problem. If your primary refrigerant leaks out, it is hazardous to your health and to the environment, while secondary refrigerant is not so harmful. So quantity of the refrigerant required is less, quantity of the refrigerant required is more, because it is working on the phase change process. The primary amount of primary refrigerant required is normally smaller, but because the secondary refrigerant works on the sensible heat, so the amount of secondary refrigerant required is normally larger. It works on a larger mass flow rate. No antifreeze is required. Your primary refrigerant can go as down as -40, -50 degrees centigrade, and it will not require any antifreeze substance to it. But in case of the secondary refrigerant, sometime you may have to use a secondary an antifreeze. Like in case of a ice plant, we use water with the salt solution, 70% water, 30% salt solution, so that the freezing point of the water, which is 0 degrees centigrade, can be moved down to as low as -35 to 40 degrees centigrade. So that way you can use that brine to make ice. Otherwise you cannot. So an antifreeze is sometimes required in case of a secondary refrigerant, and it is not required in case of a primary refrigerant. Okay, may or may not be corrosive, usually corrosive, because it is involving water and solution of water, so you can imagine, so most of the time it is corrosive. Example of primary refrigerant is your R11, R12, R22, R134A, and ammonia and carbon dioxide. Those are the primary refrigerants, and the secondary refrigerants are water, brine, or glycol, solution of water. Okay, So that is a comparison between a primary refrigerant and a secondary refrigerant. Now the classification of the refrigerant, of the primary refrigerant I should say. Okay, the refrigerants may broadly be classified into the following two groups. Primary refrigerants and secondary refrigerants. So primary refrigerants generally are further classified into four classes of elements or compounds: halocarbons, hydrocarbons, organic and inorganic. Later on we will see that basically the primary refrigerant can be classified only in organic and inorganic, because hydrocarbons and halocarbons are basically organic compounds. So let's moving on. Number one is the halocarbon refrigerant. The halocarbon compounds are all synthetically produced and were developed as Freon family of refrigerants. Such refrigerants are fluorinated hydrocarbons derived from methane, ethane, etc. So basically hydrocarbons are mixed with the halogen group number 7 on your periodic table. Then we get the halocarbon. And there's two types: completely halogenized and partially halogenized halocarbons. So we will look into that one. So this is halocarbon refrigerants. Okay, so the examples are R11, R12, these are the famous one, R22, which is monochloro difluoromethane. This is the formula, chemical formula on your right hand side. So moving on, the next group is the hydrocarbons, HC, which is the organic compound also. Most of the hydrocarbons refrigerants are successfully used in industrial and commercial installation. They possess satisfactory thermodynamic properties but are highly flammable and explosive. As you can imagine, all hydrocarbons, whether methane, ethane, propane, butane, they are all flammable. They easily catch fire. But because they have very good property as compared, it doesn't affect your atmosphere, your environment. Environmentally very, very safe, but very flammable. So it has a disadvantage of being flammable, but otherwise it doesn't affect your environment. That's why they can be used as a refrigerant. The various hydrocarbon refrigerants are given in the following table. So R170, R600 is quite popular these days, butane, and R290 is also very, very much in use in European countries and in America, but not in Pakistan. In Pakistan we are still using the halocarbons. HCF 134A is what we are using here, and 22 we are using R22 and R40. The third is the organic compounds. So these are hydrocarbons. HCs are also organic compounds, but these are organic compounds, but these are the other ones. They are hydrocarbons with ethylene and propylene base. Examples include R1120, trichloroethylene, C2H4Cl3, or R1130, which is dichloroethylene. So these are longer ones than what we have included here. Okay. So the fourth group is the azotropes refrigerants. Azotropes are basically mixtures of two refrigerants. The term azotrope refers to a stable mixture. That is, stable means if you heat them, if you vaporize them, the composition of the mixture will stay the same. This is a mixture. Azotropes are basically mixture of two hydrocarbon refrigerant or halocarbon refrigerant. Okay, but they cannot be separated by distillation process. Even though if they go through phase change process in the refrigerating circuit, they will still be same ratio of the two components will be there, or three components will be there. Okay, they cannot be separated. So then we call azotrope. The other ones which get separated by distillation is called zeotropes. So this azotropes. Okay, the term azotropes refers to a stable mixture of refrigerants whose vapor and liquid retain identical composition over a wide range of temperatures. However, these mixtures usually have properties that differ from either of their components. So they have a different boiling point and different freezing point as compared to their ingredients, their original components. So the mixture will have different physical property than the constituents. Okay. Azeotropic mixtures are designated by 500 series. Some of the azotropes are listed below. So R500 is basically a mixture of R12 and R152. in the ratio of 73.8% and 26.2%. So these are basically mixtures of two different refrigerants. R500, R502, 503, 504, they're all mixtures of two different refrigerants. Okay, zeotropic blends, as I said, they can be separated by the distillation process, which change composition when boiled at constant pressure, and so can be separated into their components by distillations. They can be separated into their components by distillations. The azotropes cannot be. These are used extensively in absorption systems. Zeotropic refrigerants are designated by 400 series. So I've given you some examples of zeotropes here, like R404A, R407C, etc. And these are mixtures of three different refrigerants in the ratio of 44%, 52%, and 4%. Okay, so these are the zeotropic. Zeotropics, the difference is that zeotropes will separate as it goes through the phase change process. Okay, azeotrope will not. So moving on, inorganic refrigerants. Now, the inorganic refrigerants is what the refrigerating system first started with. The first refrigerants were the inorganic ones, and then we started using the organic ones. So the inorganic refrigerants were exclusively used before the introduction of halocarbon refrigerants. So they were the only ones that we were using before the halocarbons. Okay. These refrigerants are still in use due to their inherent thermodynamic and physical properties. Inorganic compounds are designated by adding 700 to their molecular mass. That is, water, the molecular weight is 18, so add 7 in front of it, so it will become 718. Ammonia's molecular weight is 17, then add 7 in front of it, and so on and so forth. So carbon dioxide is 744 and sulfur dioxide is 764. So that's how we designated them in our refrigeration system. So inorganic refrigerants. The refrigerants are either organic or inorganic compounds. Amongst the organic compounds, these can be either hydrocarbons or halocarbons. So hydrocarbons are the plain one, simple one, and halocarbons are which are being mixed with the halogen group of periodic table, which is group number 7. Halocarbons contain apart from hydrocarbon and hydrogen, from carbon and hydrogen. So the elements of halocarbon group such as fluorine, chlorine, bromine, iodine, and astatine, which are part of the group 7A of the periodic table. Chlorofluorocarbons contains apart from carbon and hydrogen the elements of chlorine and fluorine. So that's why it is HC mixed with chlorine and fluorine, two of the halogen element. All halocarbons containing chlorine and bromine cause ozone depletion. Now the story starts on the environmental effect. How does these halocarbons affect your environment? The inorganic ones are not so dangerous for the environment, as they are dangerous because of their flammability or because of their toxicity. But other than that, they are not so dangerous to the environment. But these halocarbons are dangerous to the environment in two ways: that they can deplete your ozone layer in the upper atmosphere, or they can act as a greenhouse gases and raise the temperature of the Earth's surface. So there is two ways that they affect your environment, and we need to mitigate those effects. All halocarbons containing chlorine and bromine cause ozone depletion. Fluorine does not cause ozone depletion, but it is a greenhouse gas. So it is its effect, its ODP may be 0, but it is its other one. The greenhouse effect is much larger. So we have to find a replacement for it. The chlorine and bromine containing compounds causes maximum ozone depletion. In view of these facts, the new classification of the organic refrigerants is as follows. So initially we started with HC, then mix fluorine with the HC, it becomes fluorocarbons. Then mix hydrofluorocarbon. This one completely removing the hydrogen. So fluorocarbons, this one with the hydrogen. So it's hydrofluorocarbon, and this is hydrochlorofluorocarbon. So it has a fluorine atom and a chlorine atom, both hydrochlorofluorocarbon. And CFC was chlorofluorocarbon. HFC is hydrofluorocarbon. So this one does not have hydrofluorocarbon. Okay, and this is chlorine atom with the hydrogen atom, hydrochlorofluorocarbon. It is the chlorine atom which is depleting the ozone layer. So the initially it was an effort to remove the chlorine from the refrigerant. So this hydrofluorocarbon is one of that effort where chlorine has been replaced. So initially it was CFC, which is chlorofluorocarbon. So it has fluorine, but we wanted to remove chlorine because it was affecting the ozone layer. So we came up with the HCFC, which is lighter. It is also damaging the upper atmosphere, the ozone layer, but not as much. So further removing the chlorine, it becomes HFC. So in case of HFC, it has the ozone depletion potential almost zero, but the fluorine is a greenhouse gas, so its global warming potential is kind of higher. It's much higher than the carbon dioxide. So that's why this is HFC is our famous refrigerant R134A is also an HFC. So now there is an effort to find an alternative to that, which are turning out to be the hydrocarbons and one more other refrigerant that is under investigation to replace it. So the primary refrigerants thermodynamic characteristics is should have high latent enthalpy of vaporization, because we want to utilize the latent heat of vaporization, so it can absorb much of the heat from the system and expel it to outside. This means a larger refrigerating effect per unit mass of the refrigerant circulated can be achieved if it has higher latent enthalpy of vaporization. Low freezing temperature. The refrigerant must not solidify during the normal operating conditions. As you know, in your refrigerator, the temperature can go as low as minus 25 degrees centigrade. So your refrigerant must be capable of not freezing at that temperature. So it should be the freezing point should be much lower than that. Relatively high critical temperature. If relatively high critical temperature, then the power required to compress it will be lower. The large amounts of power would otherwise be required for compression if it has low critical temperature. Positive evaporating pressure. That is, when it is evaporating, it should evaporate higher than the atmospheric pressure. Otherwise, if it evaporates lower than the atmospheric pressure, then what happens is that if your system got a leak, or if your evaporator has a leak, then the air will leak into it and you will not know. But if it is working on a higher pressure, higher than the environment pressure, atmospheric pressure, higher than 100 kilopascal or 1 atm, then if there is a leakage, then the refrigerant will try to escape into the environment. In that way, there will be hissing sound, and that can be easily identified and repaired. So that's why we want positive evaporating pressure. Okay, fifth one is relatively low condensing pressure. Otherwise, expensive piping equipment will be required. So we want condenser will always have high pressure, but it should be relatively smaller. If it's too high of a pressure we have to deal with, then the cost of manufacturing condenser or the material required to make condenser will be much higher. So moving on, the physical and chemical characteristics. Number one, it should be a high dielectric strength of vapor, because your refrigerant is, after circulating from the evaporator, it is going into the condenser and into the compressor, and the normal compressor that we are using is a hermetic type compressor, where the motor is inside the compressor. It is not out of the compressor. Motor is inside it. So, and the lubricating oil is also in the same swamp, and refrigerant in the vapor form will also enter in the same casing. So it should have, because the motor's winding is open into the lubricating oil to keep it cooler, and the refrigerant is also entering there. So it should have a high dielectric strength of vapor. Otherwise, it will react with the open winding of the compressor motor, and that will be damaging for the motor. So that's why it should have high dielectric. It should not react with the current or the circuitry inside the motor. Good heat transfer characteristics. Thermophysical properties, density, specific heat, thermal conductivity, and viscosity should be such that high heat transfer coefficients can be obtained, because when your refrigerant is going to the condenser or the evaporator, which are the two heat exchangers, then it should have a higher thermal conductivity, so that can either absorb more heat in case of evaporator, or in case of condenser it can expel more heat into the environment. So high thermal conductivity is a requirement. So for the same reason, viscosity, higher viscosity and specific heat is required. Satisfactory oil solubility. So this is one of the criteria which is very much important. Initially when carbon CFC was used, chlorofluorocarbon were used, the lubricating oil was the mineral oil. But when we replace it with the halogen group, adding with the halocarbons, HCF, so in that case the mineral oil could not be used, because mineral oil is not soluble into the halocarbons, so they stay separate. So if it does that, then it obstructs in the working of the lubricant of the compressor. It cannot let lubricant to either lubricate very well the piston cylinder arrangement there, or to expel heat from the from the casing of the hermetic compressor outside, because in between is this refrigerant staying. So mixing of it or solubility of it in the oil is very, very essential from that point of view. And another point there is that no matter how hard you try, but some of the lubricating oil will escape from the piston cylinder arrangement, even though with the piston you have oil ring in there to avoid the oil getting into your chamber, in your compression chamber, but still some of the oil will leak out from. If the compressor is new, then probably not much, but if the compressor is getting older, the ring piston ring is getting weaker and weaker, then some of the oil will escape out from there and it will go into the refrigerating circuit with the refrigerant. Okay, so now if the refrigerant and the lubricating oil is not soluble in each other, then the oil which has escaped will never come back to the compressor. If it is mixed up, then what will happen, as the refrigerant is traveling throughout the refrigerating circuit, after compressor it will go to the condenser, then expansion valve, then the evaporator, and then it will come back to the compressor. Oil will follow the same route and it will come back if it is soluble. If it is not, then it will stay either in your condenser or in your evaporator, wherever it get to. And then because these lubricating oils normally are not as thermal conductive as the refrigerant itself, so it will act as an insulator, and it will reduce the refrigerating capacity of your system. So that's the other reason. One more apparatus that we use with it is the oil separator. After the compressor, normally there is an oil separator also installed because of the same purpose. If some oil escapes from the hermetic compressor, then it can be captured just after the compressor, before it goes to the condenser, and then return it back to the compressor. So that is the story here. An oil separator placed in the start gas line removes oil continuously and return it to the compressor where it belongs. Low water solubility. Water in a refrigerant can lead either to freeze up in the expansion device or to corrosion. So water is a no-no for your refrigerating circuit. If it gets into it, what it will do, if it travels down to the evaporator, it will freeze. It will become ice, so it will choke your evaporator. So you don't want it there. And if it goes to any other parts, it will cause corrosion. So that's why low water solubility is required. So if there is water, it should be drained out. Okay, water is not good for your refrigerating circuit. Inertness and stability. So if low water solubility, that means it will not absorb, your refrigerant will not absorb water into it. So that way, if there is some exposure, even then it will not absorb the water and take it to the circuit. Okay. Inertness and stability. The refrigerant must not react with the materials that will contact it, and its own chemical makeup must not change with time. So it should be stable. Its chemical composition should not change as it goes from phase change process, and it should be inert with the material with which it is coming into contact. That is copper in the evaporator, or aluminum in the condenser, or any other steel parts or any other plastic that it comes in contact, it should be inert. It should not react with those materials. So that's what it means, inertness with the materials. Okay, so it should not react with the other material, otherwise its composition will change and it will not be good. For it will not be as efficient as we want it to be. So normally we perform testing on the refrigerants to make sure that it will not react with the materials which are used in the refrigerating circuit. Okay, moving on. So this is the refrigerant selection criteria. What do we want our refrigerant to be? What are the characteristics of the refrigerant that we want it to be? The number one consideration is the non-flammability. So it should not combust or otherwise it will be a fire danger. Number two is the non-toxicity. So it should not be toxic, it should not be harmful to your health. The refrigerant should not be harmful to human either directly or indirectly through food stuff. So if food stuff absorbs it, then it should not harm your health either. So non-flammability and non-toxicity. The third one is the non-irritability. By mistake, if you touch it or if it gets into your eyes or nose or lungs, it should not irritate. So there is a standard refrigerant safety group classification based on ANSI ASHRAE standard. This is standard number 34, 2013. Standard number 34 they call it. The capital letter indicates the level of toxicity and the Arabic numeral denotes the level of flammability. So as you can see here, so two criteria. One is the toxicity, the other one is the flammability. So the flammability goes higher in the vertical direction, upward direction, and in X direction we have increasing toxicity. So group number A has lower toxicity, group B has higher toxicity, and then 1, 2, 3 is flammability. A1 means not toxic or not flammable. A3 is maybe non-toxic but highly flammable. That's how they've been classified. That's how they've been given. These are the standards that we use to describe whether a refrigerant is toxic or flammable. Most of the time we like it to be in the A1, it should be non-toxic and non-flammable. But this A2L and B2L are also into use because they have a lower flammability. Flame speed less than 10 centimeter per second for A2L and B2L category refrigerants. These are new refrigerants which are being investigated to replace our HCF, HFC, hydrofluorocarbon. To replace those, these are the new ones that those are under investigation to replace them. Okay, so moving on, effect on the environment. So these days the biggest criteria to select a refrigerant is its environmental effect. How does it affects the environment? So in fact, at present, the environment friendliness of the refrigerant is a major factor in deciding the usefulness of a particular refrigerant. The important environmental and safety properties are, number one is the ozone depletion potential, ODP, and the number two is the global warming potential, GWP. So let's discuss ODP first and then we will discuss the GWP. So ozone depletion potential, according to Montreal Protocol, the ODP of refrigerant should be 0. So your R134 actually has a 0 ODP. They should be non-ozone depleting substance. Refrigerants having non-zero ODP have either already been phased out, like R11 and R12 is already phased out because their ODP value is more than 0. So they are dangerous to the ozone. So that's why they are being phased out, and R22 is the second one which will be phased. Okay, since ODP depends mainly on the presence of chlorine or bromine atoms in the molecules, refrigerants having either chlorine like CFCs and HCFCs, both of them have chlorine, chlorofluorocarbon and hydrochlorofluorocarbon. So this is the chlorine atom, this is the chlorine atom. Or bromine cannot be used under the new regulations. They cannot be used, they have to be phased out. So some of them, R11, R12 are phased out, others are in line to be phased out, and they will be replaced by zero ODP refrigerant. Okay. Global warming potential. Refrigerant should have as low a GWP value as possible to minimize the problem of global warming. So in this case, in case of global warming, carbon dioxide is used as a standard. So the global warming potential of carbon dioxide is 1, and everything else is compared with that value, and then it has been given a number. So you know how dangerous it is with respect to that. In case of ODP, R11 is considered as a standard, and the R11 is been given a value of 1, and the others are compared with that. Okay. Refrigerants with 0 ODP but a high value of GWP, for example R134A. This is the refrigerant that we are normally using in our country, R134A, and this has 0 ODP, but it has a higher GWP. So that's why this is also under process of getting phased out. Total equivalent warming index. The factor TEWI considers both direct and indirect contribution of refrigerants to global warming. So to direct and indirect means directly, if it is released into the atmosphere, it becomes greenhouse gas, and indirect in a sense that when it is being used, it is using electricity or other things that are being produced using fossil fuel. So that is the indirect use of carbon dioxide for that refrigerant. So direct and indirect, the total value should be small. Naturally, refrigerant with as low a value of TEWI are preferable from global warming point. So then this is a picture which is explaining how the global warming or ODP is being created or by the refrigerant. Basically this is for CFC. So ozone depletion potential, ODP, the refrigerant potentials to deplete the ozone in the upper atmosphere should be low, and ODP value of 1 is assigned to R11. Other refrigerants are rated relative to this value. So as you can see in this diagram here, destruction of the ozone layer. As you can see it, if you use CFC, it can be leaked out into the atmosphere. When it goes to the atmosphere, rises to the upper atmosphere. Then in the upper atmosphere, it is reacting with the UV rays, and UV rays will break it up, and chlorine atom will get separated. So here it is acting with the UV rays, and the chlorine atom is getting separated. This chlorine atom acts with the ozone gas, which is oxygen molecule with 3 oxygen atom into it. So it reacts with it and breaks it down to O2. So it is damaging. It damages, it makes an hole into the ozone layer. Because of that, the UV rays, which was before stopped in the ozone layer, could not reach as much onto the Earth's surface. Now it will be reaching easily to the Earth's surface. And ozone, these UV rays, these are dangerous to the human health. They cause skin cancer. So that's the story of ozone layer destruction due to CFCs. Now global warming, GWP, the refrigerant's potential to persist in the upper atmosphere and cause greenhouse effect should be low. A GWP value of 1 is assigned to 7 to carbon dioxide, and other refrigerants are rated relative to this value. The last point is to be economics. This should be cheap, easily available. Your refrigerant should be cheaper and easily available. So this is all about refrigerants. Then I want to show you a video which will further enhance your information on the refrigerant types and its environmental effect. And after that we will discuss the designation, how to designate these refrigerants. So I would like to stop here, and then we will continue after the video. Okay, thank you.